Sometimes problems may arise also when there's a lot of biogeochemistry happening. So we have methane production or denitrification, and the gases fill up this chamber, and then that gets to the bag. It might block the flow. It causes problems for these. So there are different designs then later on having different kind of dome shape and other shapes of these chambers to avoid this problem. I would also like to mention here, while we are at this figure, that tide is plotted with a dashed line and SGD rate. So the direct measurement of SGD is the solid line. And we see that right as the tide starts falling is when we have the maximum SGD. So that's when the hydraulic gradient turns around between the aquifer and the ocean, right? So high tide pushes against the aquifer, so the hydraulic gradient is not as large as when tide starts dropping. So that's when we see maximum discharge. And that's that's a very typical setup in coastal setting. That's what you find. At low tide, you would expect the highest SGD, or low or falling tide. Another important finding from early studies was that the very early models predicted that all of the SGD would discharge as a line or either with the coastline. It was recognized that while that's not exactly the case, the reality is pretty close. In that, in a nearshore scale, where we would expect the largest SGD is right here, and so this figure shows logarithm of SGD against the logarithm of depth in the water column by Makoto Taniguchi. This one has plotted against distance. So they both show the same thing, that indeed closer to the tide line we are, the more SGD we can expect. That's where it most of it discharges. This is also confirmed by another method that's used for direct measurement, and that's by nested piezometers, where one can outfit them with temperature, salinity or conductivity and depth sensors, and just let it run over a couple of tidal cycles. And from that, it's easy to compute the hydraulic heads within these piezometers, which is plotted on here. So the red one is P1, that's the most landward, and the pink is the most seaward piezometer. And so the largest changes are experienced in the ocean side, where the high tide, low tide difference is quite big. Once we get a hydraulic head and we get hydraulic conductivity, then just simply applying Darcy's law, SGD can be, or groundwater flow can be calculated. And this very nicely shows this method allows you to measure both discharge and recharge of water in and out of the aquifer. Unfortunately, this technique is not very much applicable in Hawaii. We don't have many sandy beaches. I mean, there are some that this could be done, but we don't have all that many sandy beaches where you can pump this down deep enough to actually catch some fresh water. Another direct method is using eddy correlation techniques. The principle here is that right at above the sediment bed, current velocity, direction, and then a property such as oxygen content, temperature, or salinity is measured. And as there is turbulence from wave action and currents, there is some vigorous turbulent mixing. We know what the mixing is. It's measured by this acoustic Doppler velocity meter. That actually the measurement point is right here. That's outlined by this little cylinder. So the ADV measures the currents, their direction and magnitude, and this probe, specifically this image is from the oxygen measurement, but this has been done for salinity also and temperature. And then based on the measurements of velocity and oxygen concentration, a flux of oxygen or even fresh water, if salinity or temperature is used, can be estimated. So this was spearheaded by Peter Berg and then adapted with John Crusoe to specific SGD measurements. it seems like this would capture only a small scale, but if you incorporate the currents into this, you are actually capturing a several meter large area. So these are just a few examples that I wanted to mention to the class about direct measurements. Now let's look at some other methods that are used, and I thought it would be useful for the class to mention. And obviously, we care about terrestrial freshwater discharge, so salinity would be one of the tracers, one of the indicators that we would use. And while it's a chemical property of the water, we can actually use it also for geophysical methods, for subsurface resistivity imaging. So in a surface, obviously, an SGD, if it contains anything brackish or fresh, will alter the coastal salinity. And this is an example of a survey on the coastline in Manoa Bay, where we see spots of lighter blue. Those indicate lower salinities. And the problem with salinity is that if it is indeed SGD, then it's only the fresh fraction that you can detect, and for fresh or brackish. And in many places, like here, Pico Lagoon, it's a stream, it's not SGD. So you can't really distinguish I mean, you can obviously look at your side and see if you have any streams or surface runoff, but it doesn't distinguish between surface and groundwater inputs. But we can look at salinity in the subsurface, and that's done by electric resistivity measurement. And this is an example of streaming resistivity profile in a coral reef setting, where the idea behind this is that if you assume a homogeneous substrate, let's say porous sand, where the porosity doesn't change in space, if you fill that space, those pore spaces with fresh water, it will be much higher resistivity than if you fill that same space, those same pores with seawater, salty water. So the higher resistivity within the pores or with your measurement then indicates areas where the fresh water outcrops to the surface. And so one can put together this very nice 3D image even of, can identify outcrop locations of fresh water. And so this can be done spatially, but also on temporal scales. So looking at Kiholo Bay, this is in Kiholo Bay in Hawaii, this cable right here lays on the ground. It has several electrodes on it that can send electric signals, so the electric current into the ground. And that current will travel easier from one electrode to another if the subsurface is filled with saltier water. It will have much harder resistivity to get to the other electrode if it's filled with fresh water or if it's filled with air. So what we see on these images is the same locations. The cable was not moved, but we looked at electrical resistivity at high tide of the subsurface and at low tide. And we see that there is a big difference. So while high resistivity could be created by presence of a rock, for example, in the subsurface, and you don't know if there are rocks, that's why it's good to do this dynamically. So compare low tide, high tide. You see that these red blobs significantly increase during low tide. That means that the pore spaces are filling up. And in this case, actually, these are identified as conduits, lava tubes, and so forth. Those are filled up with fresh water at low tide. That's when the hydraulic gradient increases and the fresh water can flow out from the aquifer. Another physical technique is what you heard about already last week, is using temperature. It's because the groundwater that's recharged at higher elevation preserves its temperature signature. It's much colder than the oceans. It's the image that Craig also showed you last week, so that's his and his students' work. That shows groundwater discharge wherever we see colder temperatures than the ocean temperatures. So the ocean is the red one. The disadvantage of this technique is that it only gets the skin layer, surface. You still have to go in ground truth and see how thick that groundwater truth is, as we heard last week. All right, so let's get more into geochemical signatures. There are many different chemicals and chemical signatures that have been used to identify SGD and quantify SGD. For example, just basic isotopes of water, because groundwater isotopic hydrogen and oxygen isotopic signature is completely different from the seawater. As shown on this spot right here, this is from Sicily. Groundwater, because it's recharged at high elevation, colder temperatures, that results in more negative isotope values, is different from seawater. And then here is the submarine groundwater discharge that is a mixture of these two, so that plots very nicely along here. This is used as an alternative for salinity. This image, this figure is from work by Godoy in Brazil. They have, at this site, they have huge concentrations of nitrate, 3,000 micromoles in the groundwater, yet the bay was pristine, so they were trying to investigate whether they have potential problem in that if that groundwater discharges to the bay, they'll have significant eutrophication. So they put seepage meters down in the bay, and they collected water into the bag, and they measured the isotopes in that. And they found that indeed, they got some water filling the bags, but they identified that it was exactly the same as seawater, so it was only recirculated seawater. And after that, they discovered that the bay was actually sealed with cement from previous some industrial operations there. So that helped preventing the groundwater from discharging. So these are isotopes of water, also methane and other products of metabolic byproducts have been applied to look for SGD signature. And methane, for example, is produced copiously in anoxic environments. Its problem is, though, that it's not conservative, so it can undergo biogeochemical changes, evasion from the water to the atmosphere. Evolution is another process, so when methane is building up in the sediment, the bubble is growing, eventually it's so buoyant that it just escapes the sediment without even the advection being present. So same is true for these other gases. Nevertheless, there are examples that show very good correlation of SGD locations with methane. So that's, as an example here, we have salinity, really fresh water because of groundwater discharge here and here, also accompanied by high methane. Same very nice long time series was produced by Robert Kim on Jeju Island, where he has salinities, also radon measurements, that's another tracer, and methane. They all corroborated the same story. So in these special cases, methane was a good tracer. And then Isaac Santos uses all these other metabolites to look at SGD signatures in coral reefs. All right, so we move on to natural radioisotopes, and there are actually almost limitless possibilities on selecting these, though not just the ones that I highlighted here, but the ones I'm going to talk about are the radium isotopes, and specifically radium-226 and then radon-222. Those are, the advantage of these is that they are constantly regenerated from the rocks in the aquifer. So any groundwater we get enriched in them, and so that signature can then travel with the water and persist. And then because the particles to water ratio in the ocean is very small, the ocean has very little of these isotopes. And the application of these isotopes has been included in this very nice review by Matchrat. The idea behind the application of these is that because the non-point sources, so the SGD that's diffuse and happening over larger spatial scales, it's hard to quantify. A flux by difference approach is used. So what that means is you can identify all these other terms, and at the end, what's left over is coming from SGD, and so we can quantify SGD. And a terminal paper in the SGD history was the one by Billy Moore, who measured radium isotopes along the South Atlantic Bight, and he found that the nearshore activity in radium was quite high. It was not even, when he did the math, the rivers that bring in radium also were not able to support all that inventory that he measured. And that the groundwater indeed had very high radium concentrations. So he suggested that excess radium along the shoreline there comes from groundwater. There is still this problem with using these tracers in that what do you use as groundwater end member? Because the geology can be so heterogeneous, a karst will give a totally different isotopic signature than sand. And so how do you reconcile these differences? And some of these tracers, such as radium itself, is salinity dependent. So in fresh water, it would like to stick to particles, and in saltier groundwater, it dissolves from those particles. So salty groundwater gets enriched in it. So radium is really good in tracking salty and brackish groundwater discharge. And so how to reconcile this variation in the end member is that, for example, the advantage of radium is that there are different isotopes. You can look at different isotope ratios. And so that's specifically shown in these examples, where distinct radium signatures come from different water masses and springs. And you can even identify seawater recirculation by tidal pumping that happens on a much shorter time scale. So there is not enough time for radium to go in as much equilibrium as is for the terrestrially long-term transport of groundwater. And so that's, those are examples shown in this figure. And then once, again, this is an example from Billy Moore's-Berg. He plotted up all the marine or nearshore samples and then the wells, and then obviously you can tease out what's the percentage from each of these sources. And this is the cookbook recipe on how to actually do it with the math. So using different isotopic signatures, identify fractions of fresh water, recirculated seawater, and ocean water. And I said I wouldn't talk much about nitrogen fluxes, but I would make this extension because this represents very well the idea that if we, for example, use radium and we get radium flux or HGD fluxes using radium, and if the nutrients here shown total dissolved nitrogen or total dissolved phosphorus are well correlated with that radium, then the radium flux obviously can be converted into nutrient fluxes. And so the South Atlantic Bight was one example. This is another example that Craig already mentioned. These tracers can be actually applied for all ocean scale. So this is the example that Craig mentioned for the Atlantic Ocean, or based on all of the geosacks and other sampling events. Let's skip this. Following up that study, which was done in 2008, a much newer paper in 2014 by Kwan et al., they actually expanded this technique out to the Pacific and Indian Ocean. And the conclusion for both of these papers is that the total HGD, so not the terrestrial fresh, but the total HGD is, well, for the Atlantic was 1.62 times more than the river fluxes. For the Pacific and Indian Oceans, total HGD is 3 to 4 times larger than the river discharge. So indeed, it is applicable for large-scale studies, and it also shows that HGD is pretty important. And then very quickly about radon, which is also one of the earliest applied tracers. Also in '96, Jay Cable published this findings that they looked at the Gulf of Mexico, where there was a isolated surface layer that didn't have much radon, but then the deeper water column had a radon excess that when they calculated if it could be supported by diffusion from the sediments or simply diffusion, no attraction present, it could not. There was much more excess radon that could be explained by diffusion, so it must be coming from SGD. And so they indeed looked at the sediment depth profiles of radon and found an equation that fit their data, and which showed not just diffusion as an important transport process, but also advection. And so this example I wanted to include because it shows the really small scale to the much larger scale that can be applied. And I'm not going to go into these details, but we'll go into my last 3 slides, running out of time, sorry. So, what I feel the new trends in SGD assessments are that we need long-term records, we need to know large-scale occurrence of SGD, we need it all in high resolution, and of course, if possible, real time. Like we have salinity now for all of the ocean, which is great. It's unfortunately not high enough resolution like the temperature satellites that the temperature information from the satellites that could be used for SGD. But to answer the large scale question is either using the airplane technique or actually looking at satellite coverages that have the advantage that the whole Earth is pretty much covered, so you can look at any location, and also that the imaging is cyclic, so the satellites orbit and you get an image a couple of 7 days or something like that, every 7 days. So this is an example that shows colder groundwater discharge in Ireland. Or using drones like Craig is right now spearheading in that. Advantage of this one is that you can just fly whenever, as often as you want, because once you have the instrument, you can really get nice images. And this is an example of cold plumes at Kauai Kui. So this is Manoa Bay, Kauai Kui, cold plumes that are on the coastline. For the radon sensor, I think the newest, latest, and greatest would be this submersible SubRad, which is a submersible that will be equipped by, for those of you that know the RAD7 instrument, is plotted right here. So 3 of those go in a chain and have very high sensitivity and good resolution for even deep sea dives. For radon sensing, so we are not really stuck on the embayment scale, but go into slopes and so forth. So this is spearheaded by Rick Peterson from East Carolina, South Carolina University, and Chip Breyer from Woods Hole. And this other one is our addition to the technology. It's a coastal moored system. It's called the SGD Sniffer. It can produce long-term records. It's a completely autonomous instrument. And this is an example record from Kiholo Bay. So this is a 1-hour resolution radon. And obviously we expect this much variation because of the tidal influence of the tides influencing on SGD. So the daily average changes significantly. So that means SGD and other processes that affect the radon mass balance change seasonally. So we will have another year of data, and then we will start to look at other important trends such as sea level and precipitation and recharge rates. And I leave it at that because I already ran over time that we just allotted.
Henrietta, on that last slide, it looks like you don't see anything at high tide.
Correct, yes. The detection technique of this instrument is a little bit higher. The detection limit is a little bit higher than the usual RAD7. So we are losing some of the readings at high tide.
And is the SubRad made by Derek's company too? Or
No. Same instrument.
No, but same instrument.
Yes.
Thank you.
Could you comment a little bit more on SGD in the deep ocean? I didn't quite understand what you were actually measuring.
So, the slope scale.
Oh, no, the center of the Pacific Ocean. You had made some plots that showed
Radium signature.
ocean basin scale.
Right. So what has been done is that a total inventory of radium-228 has been measured by taking graph samples in the ocean. And once you account for what the rivers bring in, how much diffuses from the sediments, the shelf sediments, whatever is left over is then from SGD. And actually he also accounted for atmospheric inputs.
Where does the sampling take place?
So Billy Moore's work, here, every dot is a measurement. So the Atlantic is very well covered. So he was able to, I don't have that figure, the fact shows, but 3 by 3 degree grids, I think.
Yeah.
He had, so he estimated inventory of 3 by 3 degree grids.
At what depth in the ocean?
Surface.
Surface.
So presuming that most of the inputs happen into the surface mix layer. Yes, so this would not account for hydrothermal and other things that are isolated from the bottom. And then the Pacific one, the coverage is so much poorer. There are much fewer measurements. And so what they did is they actually involved a model, an ocean circulation model, to how based on those few measurements. So these are the actual measurements. So you see the Atlantic is much more densely covered. So based on these few, they made a model of radium distribution, and then again accounted for all that came from rivers and so forth to get the total SGD.
Maybe first figure that you showed, the cross section, which has measurement of salinity and nutrients. Did they correlated with geology of the site?
So
the material looks like a Meissen uniform, or
yes, so Wakiak Bay has a 10-meter thick sandy top layer that's homogeneous. So you can, yes. That's why all the many examples that I use, the textbook examples and how it should behave come from there because it's so uniform.
That's a really porous wetland environment over there too. Yeah.
It's so that part is all sandy.
Oh, okay. So it's not in the
Not clay.
wetlands.
No.
Because those have incredible amount of flow through them as well.
Also, yes. But they have a complexity of the clay layers and whatnot, but Wakiak Bay doesn't have that. So the shallowest clay layer is 10 meters, I think. Any other questions?
It's a bit off topic, but one of your last slides you showed a map of the world's salinity.
Mm-hmm.
Is that remotely sensed?
Yes.
Or?
So now it's relatively new, couple of years now that it's available.
And is that based on density of water, or how?
No. That's wavelength. So they measure certain wavelengths. I'm not exactly sure, but they have a big antenna on the satellite and they collect. Any remote sensing experts here? So anyway, you can look it up online. I don't exactly know how that satellite works, but the resolution apparently cannot be improved because the antenna that they would need would have to be huge.
Mm-hmm.
So right now it's a kilometer or so.
Which technique is more accurate to quantify SGD?
It depends what you want to know. The scale, how large of the scale, how close to the shore. Usually it's a combination of techniques. It's what I would recommend, what we also do. You do several things first to scout out the whole area, where do I have the maximum fluxes, where I have what's the variation, and you combine things.
For example, for small scale.
Well, I like to use radon, obviously. I like to use radon because it gives you the spatial and temporal resolution of the near shore environment. And so you're not just doing a spot measurement, but it integrates the signature over a couple of tensile meters depending on the physical oceanography. But that's not enough because it captures total SGD, so you still don't know how much fresh, so you definitely add the freshwater part, the salinity measurements to it. You need to know the N numbers, so you put in piezometers, and then you might as well measure the hydraulic head there, the gradient. So it's always a combination. There's no straight answer.
Okay, all right, everybody. So those of you in the class, take a 15-minute break. We'll be back in 7:02 across the way. And we're going to do a practical computer science. Yeah. You gotta finish that story.
Oh, you have to get your own.
Are you going to check my wall?
Well, you will be presenting this year workshop at the end.
White with white.
Let's go to the same option.